So we are given a question. Question is, let f be an integrable function. Show that for all epsilon greater than 0, there exists g continuous such that g equals 0 outside a finite interval and such that integral of mod of f minus g dx is less than epsilon. So in the question, it is asking that uh, suppose you have a function which is integrable over real line. So there exists a continuous function g such that integral of mod of f minus g is less than epsilon. Okay, so we have only just one thing, we only have the integrability of f. Okay, now how we'll show this? So firstly, I will tell you the strategy that what we are gonna do, and after that we will formally write the proof of this in a formal and organized manner. Okay. In the hypothesis, we only have integrability of f on R. We only have integrability of f on R. Okay. What it means? It means that over R, mod of fx dx is less than finite. Okay. It means it means that suppose you have real line. Suppose you have this real line. You have this real line. It means that for any epsilon greater than 0, you can choose any finite and large interval. Say it is minus r to r, minus r to r. It is finite and large in such a way that the contribution of the region outside this interval is less than epsilon by 2. It is for any epsilon. For any epsilon greater than 0, you have this thing. Okay. Now, this is the story all about the region outside minus r to r. Then what about in the region minus r to r? Okay. So, what we're gonna do in the region minus r to r, we will approximate this function fx by a simple function. Then the final output will look like this. This will look like for r mod of fx minus phi x dx. It is a simple function. It will be less than epsilon by 4. Okay. Then we have approximation in the region outside minus r to r and inside the region minus r to r. Okay, so we have covered all the real line. We have covered the whole real line. So fx minus phi x dx will be r plus it is okay. So it is less than epsilon by 4. It is less than epsilon by 2. It will be less than 3 epsilon by 4. Now our third step will be then our third step will be to approximate this function, this step function, by a continuous function gx in like this: phi x minus gx integral dx over whole r will be less than epsilon by 4. Then by using the triangle inequality, we will show this. We will show f minus g dx less than epsilon. So we'll write the proof. The proof will be, let f be an integrable function on R. So it is measurable and finite almost everywhere. So fx dx is finite over whole real line. So it means for any epsilon greater than 0, we can find a large and finite interval minus r to r in such a way that the contribution of this region minus r to r of this region to the integral is very small. So specifically we can choose R positive such that fx dx it is such that fx dx is less than epsilon by 2. Mark this in equation as 1. Next, we will approximate f by a simple function. You may define simple function also. A simple function is defined as a non-negative finite valued function taking only a finite number of different values is called a simple function. Okay, it is defined as what? Phi x equals ai's chi of ax, I is from 1 to n. Okay, where chi I is a characteristic function of a measurable sets EI and AIs are constants that approximates fx on each EI. EI is a subset of minus R to R. Now, by partitioning minus R to R into sufficiently fine intervals or sets, we can ensure that in the region minus R to R, fx minus phi x dx is less than epsilon by 4. Clear? So over whole R, fx minus phi x dx will be what? Plus how f was approximated in the region outside R, it is by fx dx, and what about the region inside R, it is fx minus phi x dx. Clear? So by inequality first you will get it is less than epsilon by 2, and by this inequality you will have epsilon by 4, so you will have 3 epsilon by 4. Mark this inequality as 2. Now our next and the final step is to approximate the step function phi x by a continuous function gx. Okay, so how we will gonna do? We will do like this. Since phi x is a step function, so it is continuous, so it is discontinuous. So now we will construct a continuous function g that approximates this phi closely. Okay. So I'll tell you the strategy that how we're gonna approximate this phi by this g. Okay, we will approximate this step function phi by g by constructing g with the help of bump functions. Okay, so bump functions are like characteristic functions, means they look exactly the same, but their behaviors on the boundary is different. Let me tell you how they behave differently. gi is all, say gi is a bump function, so gi is also 1 on ei and 0 outside ei, and characteristic function also, it is also 1 inside e and outside it is 0. So they all are similar, but the only difference between these two functions is that this function gix is infinitely differentiable over ei, inside ei, and behaves very smoothly on the boundary. Okay, whereas in the characteristic function there is a sudden shift on the boundary of ei. Okay, so the only difference between gix and this characteristic function is the transitioning of the function on the boundary. That's the only difference. So this gix will be constructed like gx will be gx will be summation I from 1 to n ai gix. This finite linear combination of this bump function will be our gx. Okay, and what it is, phi x is what? Phi x is I from 1 to n ai chi eix. Okay, then phi x minus gx is what? It will be summation I from 1 to n ai gix minus chi eix. So what? Inside ei gix and chi eix are same. The only difference is in the transitioning. So this will this term, when n tends to infinity, will go arbitrarily close. So this will tends to what? This integral will tends to what? 0. So this step function gets approximated by this continuous function. Okay, so how we will write? We'll write since phi is a constant on each set ei, so we can replace each characteristic function by a smooth bump function. Smooth bump function gix, which approximates characteristic function closely. GIs, chi EIs. Okay, so you can write the definition of GI here. So GI is what? GIX is 1 0, x is in A, and outside A it is 0. So what? GIX is 1 inside A, and outside A it is 0. Okay, so each GIX can be chosen to be continuous and vanish outside minus R to R. This smooth approximation will yield a continuous function g, which is supported on minus R to R and approximates phi x. And what is gx? Gx will be I from 1 to n ai gix. Okay, so this finite linear combination of gix will be our gx. Okay, and this gx will approximate phi x on minus R to R. By construction, gx is continuous and supported on minus R to R, meaning gx is 0 or vanish outside. Gx is identically 0 identically 0, outside minus R to R. Additionally, we can choose a smooth bump function gix in such a way that integral over minus R to R phi x minus gx is less than epsilon by 2. Okay, mark it as 3. So over R fx minus gx dx equals what? Equals integral fx minus phi x dx over R plus over R fx minus gx minus phi x dx. Okay, it is by triangle inequality. Clear? So by in equation 2 we have it is less than 3 epsilon by 4. 3 epsilon by 4, mark it as epsilon by 4. Okay, it is epsilon by 4, and by in equation 3 we have epsilon by 4. So what it will have? We have epsilon. So the thing to notice is that here we are taking the integral over R, and here we have taken the integral over minus R to R. This is because outside this region, this integral will vanish. So this thing and this thing will come same. So this thing will be less than epsilon. So integral of fx minus gx dx is less than epsilon on R, or f minus g dx is less than epsilon.